Thank you. I'll begin with a prayer. Heavenly Father, we thank you for this day. And Lord, I thank you for the students. I pray that you just bless our time together. Help us again, Lord, to glorify you in what we do this day, Lord. In your name I pray. Amen. So you guys, is there any particular homework question you'd like to talk about? Yeah. Anybody else? Which section? 12.9. Number 20? Sure, we can look at that. Number 20 of 12.9 asks us to expand f of x in powers of x, basing your calculations on the tangent series. Now here's something we haven't derived yet, so I probably should explain where the tangent series comes from after we get on with this problem here. But, oh, wait a minute. I'm sorry. I've read the wrong instructions. Where are we? 11 through 22. Oh, we're just supposed to expand f of x in powers of x. So, let's see here. What's our f of x? Oh, I don't know why I wrote that. F of x equals to, where was I? X squared plus x times the natural log of 1 plus x. Let's see here. What I would probably do here is I would attack log of x by its lonesome. So let g of x equal to the natural log of 1 plus x, right? So that gives me that dg dx is 1 over 1 plus x, which is otherwise known as the sum n equals 0 to infinity minus 1 to the n, x to the n, right? And then I integrate to get back to the natural log of 1 plus x is equal to some constant plus the sum n equals 0 to infinity minus 1 to the n, x to the n plus 1 over n plus 1, but setting x equals to 0 yields c equals to 0, hence the log of 1 plus x is the sum n equals 0 to infinity minus 1 to the n, x to the n plus 1 over n plus 1. Now you should recognize this as being a subcase of the example we worked at the end of class yesterday. Kinda. I guess there we did log x, didn't we? Right? So you could obtain this series from the example I did last class by a substitution. Let me just pause to do that for a second before I go on with this problem. What did we find last class? We found that the natural log of x is equal to what? The natural log of a, right? Plus the sum, what was it? N equals 1 to infinity. How'd it go? Minus 1 to the n. You guys have to help me out here. I don't remember it exactly. N times a to the n. X minus a to the n. Is that it? I mean, help me out if I... Is n plus 1 here? So we derived that yesterday, right? So one way we could look at this problem is we could use that. let's see here. My shirt needs a wash. Let's see here. So this other one, in other words, the log of u is the natural log of a, plus the sum n equals 1 to infinity minus 1 to the n plus 1 over n times a to the n, right? So how would I get from like this to log of 1 plus x if I wanted to do it this way instead? To break down what I'm doing right now, I'm showing you two different ways to find your way to the log series. Once we have that out of our system, I'll come back to the original homework problem that was asked, and I'll finish it. I just want to stop and focus on the log here for just a minute. Make a connection, yeah. Okay. So if I want this to be the natural log of 1 plus x, right? What's that say? I make u equal to 1 plus x, right? And if I make u equal to 1 plus x, that says that I want u minus 1 to be like x, right? Which suggests what? Looks like I should choose, well, oh. Yeah, a equal to 1, right? Excuse me, and then that gives me log of 1 plus x equals to what? Log of 1, which is 0, right? A to the 1 to the n is just that, and u minus a was what? Well, u minus 1, this is x to the n. And you could rewrite this as the sum, what did I do? Oh, I'm sorry, I was about to get really confused. So k, we could say k equals 0 to infinity, minus 1 to the, let's see here. I want to let n equal to k plus 1, just to make them look the same. So like, that makes n plus 1 equal to k plus 2. So minus 1 to the k plus 2, which of course I could, minus 1 to the k plus 2 is really just what? Minus 1 to the k. And n is k plus 1, and that's x to the k plus 1. So you can see that this and what we found over here by geometric series is the same animal. So my point is, if you remember the thing we worked out last time, you could make a substitution to find the power series for log of 1 plus x. I don't know. I guess the power series, the Maclaurin series for the log of 1 plus x is a pretty standard example. So you should feel free to quote it in your homework, but you should also know how to derive it either this way or that way. But that way's longer because you had to go back to what we did last class too, right? Yeah.
You took the 1 away from the k, from the negative 1 to the k. Where do you get the n minus 1 from? Like you said you'd get the k from the n minus 1, but it's n plus 1. So, you see where it's like negative 1 to the k? You took away the positive 1.
Well, I said this was actually k plus 2, making the direct substitution to start with, but, because n plus 1 equals to k plus 2. But the thing is, minus 1 to the k plus 2 is minus 1 to the k times minus 1 to the 2, which is minus 1 to the k, which is why I had done this a second ago. Yeah. I just wanted to show you that they are the same thing. All right. Sorry, I have spent entirely too much time on this example at this point. Not this example, but the log of 1 plus x issue. All right, let's just stick a stake in its heart. It's done. All right, so we now know that this is equal to x squared plus x times the sum n equals 0 to infinity minus 1 to the n x to the n plus 1 over n plus 1. And I'm supposed to find the power series for this function centered at x. See, once I find the power series for log x, then the rest of this becomes pretty routine, right? Because now I just have to multiply, right? And so we can distribute, we have x squared times the sum and then plus x times the sum, right? Then you bring the x in. So what we have then is we've got the sum n equals 0 to infinity minus 1 to the n x to the, looks like n plus 3 divided by n plus 1 plus the sum n equals 0 to infinity minus 1 to the n x to the, looks like n plus 2 over n plus 1. Right? Do you guys agree? And we're not done yet, yeah.
So in the homework you made, when you reached this point, you made a J substitution. Was that necessary?
If I want to have a nice answer, yeah. I mean, these are overlapping. So like this isn't really, I'm not done sort of putting away the dishes, let's say. I mean, it's not cleaned up yet. The sum of two power series, we can rewrite it as a sum of one power series. That's why I make a J substitution there. Let's see, this one starts at what? You look at this, this starts at x cubed, right? This one starts at where? At x squared, right? Times the coefficient. So what I'm going to do is I'm going to peel off that first one there, and I'm going to rewrite this as, let's see, when I put in n equals 0 into this the right sum, what do I get? Just x squared, right? Just plain old x squared. So I get x squared plus, all right. And so if let me just, if you don't mind, I'm getting tired of writing. So if I want to, I could put a 1 here and say plus x squared, if that would be okay with you guys, just to emphasize. Now this starts at x cubed with that modification, all right? The point of doing that is then I can make a substitution. I can make a substitution now. Let's let j equal n plus 3 for this one. Let's j equal to n plus 2 for that one. So this makes n equal to j minus 3. For this one, the game is n is equal to j minus 2. So I have the sum j equals to, let's see here. If n starts at 0, j starts where? 3, right? And then I've done this so that I have an x to the j out here. All right? So this, I get minus 1 to the n, which was j minus 3. And then n plus 1 is actually what? J minus 2, okay. And then plus minus 1 to the, let's see over there. Minus 1 to the, what is that? N is what? N is j minus 2. And n plus 1 is what? N plus 1 is j minus 1. Of course, we can clean this up a little bit more. Let me do that. This is x squared plus the sum. J equals 3 to infinity of, let's see here, I guess I can just rewrite that as minus 1 to the j, right? Times 1 over j minus 2 plus what? Plus or well minus, right? No, plus. Well, oh, I'm sorry, other way around. So this should be j minus 1. I like to write I'm going to write this one first, and then minus 1 over j minus 2. All x to the power j. And that's how I would write the answer. I would give significant partial credit for getting to here. Right. But this is, I think, maybe the best answer. And this answer allows you to answer questions like, what's the 100th derivative of this function, right? Like, what's f100 of 0? You see what I do is I just say, okay, so f100 of 0 over 100 factorial is equal to whatever the coefficient of x to the 100 is. And I can see what that is pretty easily here from that. It's, minus 1 to the 100 times what? 1 over 99 minus 1 over 98. So the 100th derivative evaluated at 0 would be 100 factorial divided by 99 minus 100 factorial divided by 98. You could simplify that a little bit, right? But I'll just leave it like that. I mean, whatever. You could factor the 100 factorial out. I mean, you could do... Now, you could still do that calculation with the significant partial credit answer, but then you'd have to sort through what are the different possible ways to get 100 power, right? I could get 100 from n equals 97 here. I could get 100 from n equals 98 here. Putting everything together just gives me a proper answer. This is the power series for the log of 1 plus x times x plus x squared. Yeah. Other questions, guys? Let's see here. Did I ever tell you guys about, let's see here, division? Let's talk about division. So what if we wanted to calculate like sine x over cosine x? Suppose we wanted to find a power series of that. So what would we have? We'd have x minus 1/6 x cubed plus 1 over 120 x to the 5th plus dot 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 dot, right? And then downstairs we've got 1 minus 1/2 x squared plus 1 over 24 x to the 4th and stuff. Let's see here. Let's try to look at how we do division of series. So just a reminder, if I had 100 and I'm dividing by 24, by 17, how do I do it? I do put the 100 here, right? I put the 17 over here, and so forth. So same kind of song and dance here. I put the thing I'm dividing over here, dividing by. I put the cosine over here, I put the sine in here. But otherwise, I pretty much follow the rules of long division that you know and love from your childhood. Let's see here. So 1. But just like usual with power series, you have to keep track of how many terms you want. And if you don't keep enough at the start, then you have to go back and adjust and blah, 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 blah. I'll just do the first few terms here. Let's see here. To get started, what do I have to put? X, right? So if I put an x here, and then I have to multiply my cosine series by x. So that gives me x minus 1/2 x cubed plus 1 over 24, x to the 5th plus dot dot dot. I take the difference of those, right? What's that give me? Right, I get 3/6 minus 1/6, which gives me 1/3, right? So 1/3 x cubed. And that's 5/120ths. So minus 4 over 120, which is minus 1/30th, I think. You guys correct me if I'm wrong on that, would you? I'd appreciate it. Am I right on the minus 1/30th? Okay. And then, so what comes next then? I gotta take something times the cosine series to get this 1/3 x cubed, right? It's pretty easy to figure it out. I have to do what? Plus 1/3 x cubed, right? Yeah. So what's that give me then? So multiplying that by 1/3 x cubed gives me 1/3 x cubed. Good. 1/3 times 1/2 is minus 1/6 x to the 5th, and then plus stuff I don't care. All right, take the difference of these. What do you got? Here we got 5/30ths. Here we have 1/30th. So it looks like 5 minus 1, right? 4/30ths, 2/15ths, eh? Am I right? 2/15ths x to the 15th. X, did I do it wrong? Es bueno, es no bueno. It's good. Let me check something. Where'd that go? Oh, okay, good. Yeah. And so then you know what happens. The next thing you put is plus 2/15ths x to the 5th, and so forth, right? And so forth. It keeps going and going and going and going and going, right? But anyway, there you go. So therefore, the tangent Maclaurin series is equal to x plus 1/3 x cubed plus 2/5 x to the 5th, 2/15ths rather, sorry, plus dot 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 dot. See, I think that's pretty nice, right? I mean, that's I think it's really pretty that we can divide power series just like we divide numbers, right? We just have to be careful. Yeah.
Does this work like cleanly only for trig functions and hyperbolic trig functions?
No, we can divide any two power series and see what happens. Yeah.
This wouldn't be clean.
I don't think this is particularly clean, honestly. I can show you really, really clean in a contrived way. I have an example somewhere, but let's not do that. Like, excuse me. Oh, once you have this, we can do other examples. Like, suppose you want the power series for secant squared. So what is secant squared? The derivative of tangent? Yeah, so that's why you were telling me 1 plus what? Yeah, 1 plus x squared plus, you say 2/3? X to the 4th? Yeah. So there's another fun one. Do you guys have other questions about anything in particular? All right, well, let me show you another example. So let's say expand f of x equal to the sine of x I'll tell you, I'll make it more fun. Let's make it the sine of 3x at x equals to 2. Now you could use Taylor's theorem here, but I like to do it the following way. Actually, let me make it so that Taylor's theorem would be painful. I'll just put an x here. There. That makes Taylor's theorem really unpleasant. It also makes this problem significantly more unpleasant, but we'll deal with it. Okay, so basically the trick is just to replace x with x minus 2 plus 2. All right, so to expand on that, that's x minus 2 plus 2. I'll leave this alone out here to start with. And that's the sine of 3 times x minus 2 plus 6, right? Excuse me. Unpleasant. Let's see here. All right, so this, we know adding angles formulas for sine, right? So this we could do what? So this is sine of 3 times x minus 2, cosine of 6, plus the cosine of 3x minus 2, sine of 6. So I can rewrite this whole thing as x minus 2 plus 2 times like cosine of 6 times the sum, n equals 0 to infinity, of minus 1 to the n, 3 to the 2n plus 1, x minus 2 to the 2n plus 1, divided by 2n plus 1 factorial, plus the sine of 6 times the sum, n equals 0 to infinity, minus 1 to the n, 3 to the 2n, x minus 2 to the 2n, divided by 2n factorial. And then the unpleasant thing is, you see what's so unpleasant is now I have to multiply x minus 2 onto both things and 2 onto both things, right? Maybe before I go further, any questions about what we're doing? Why not just use Taylor's theorem? Why not just differentiate and plug in 2? I mean, that would be fine if you're just looking for the first few terms, right? It wouldn't cost you too much thinking. But if you want the complete power series, you got to do something like this, I suppose. All right, so we got cosine of 6 times the sum, n equals 0 to infinity, minus 1 to the n, 3 to the 2n plus 1, times x to x minus 2 to the 2n plus 2, divided by 2n plus 1 factorial, plus 2 times the cosine of 6, the sum, n equals 0 to infinity, minus 1 to the n. All I'm doing is distributing, guys, 3n plus 1, x minus 2 to the 2n plus 1, divided by 2n plus 1 factorial. Then my sine terms, so I've got like sine of 6 times the sum, n equals 0 to infinity, minus 1 to the n, 3 to the 2n, x minus 2 to the 2n plus 1, divided by 2n factorial. And then finally plus 2 times the sine of 6 times the sum, n equals 0 to infinity, minus 1 to the n, 3 to the 2n, x minus 2, I'm out of board, to the 2n divided by 2n factorial. At this point, we have essentially reached sort of the analog of this step, right? Now, what should we do to really clean up the answer? We should do what? We should collect even and odd terms, right? So to get a proper answer, we should combine this and this into one big sum, and we should combine this and this into another large sum by making an appropriate substitution, right? And what are the exceptional terms that I have to pull out front? This one, these guys, this starts at 0, right? This starts at 2. So I should really pull out the 0 one from over there. I get 2 sine of 6. That's my first term. And then comparing the odd terms, I have an extra, this one, oh, do they both start at the same spot? Oh yeah, they both start at the same place. I guess I don't need to pull anything out particularly. But anyway, I'm at this point tired of this problem. Well, let's talk about something else. Unless you want me to finish it. I think I've done enough here. If you want me to finish, it'll take me another 3 minutes. We're good? Okay. You know, at this point we can answer questions with a fair amount of ease, like what's the 100th derivative evaluated at 2 of this function, right? Because that over 100 factorial should be equal to what? It should be equal to the coefficient which is next to x to the 100. Where's that coming from? I mean x minus 2 to the 100. Right here? How do you get 100 power here? You need n equal to what? 48? 49. N equals to 49. So we've got minus 1, 3 to the 99. Down here you got a 99 factorial, I think, if I've judged the pattern correctly. All of that's times the cosine of 6. Where else can you get 100 power from here? Over here, right? N equals to 50. So plus 2 sine of 6. Again, that's 3 to the 100 divided by 100 factorial. And so there you go. You can solve for the 100th derivative of f. And that's not too hard to see from the expression above, even if I don't simplify it to find the grand glorious power series answer at the end of the rainbow. Right? Again, there's nothing magical stopping us. It's just to take another minute or two in substitutions and so forth. And I judge your patience for this problem has drawn to a close, so I'm going to move on. Let's see here, guys. How about multiplying power series? How do we multiply power series? Let me multiply a couple series and see how it goes, okay? So example. How about this? 1 plus 2x plus 1/2 excuse me, plus 2x squared plus 8/6 x cubed plus dot 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 dot. Let's multiply that by 1 minus x plus 1/2 x squared minus 1/6 x cubed plus dot 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 dot. Let's multiply these series to third order. Okay? How do you do that? How do you multiply series? The way to multiply series, all right, is term by term, order by order. This is the so-called Koshi product. So what it says is to start with, you look for constant terms. What are all the possible ways you can get constant terms here? Yeah, 1 times 1. All right, so that's it. So let me just write 1. All right, and then let's say plus x times what? We have 2 times 1, right? But we also have what? Minus 1. Any other ways besides this times this or this times that? No, everything else has an x squared or higher, right? Or it's the constant term we already got. Then you move on. X squared. Were you taught to multiply polynomials like this, order by order, from least to smallest power? Least power to highest power? No, you were taught to FOIL it or something, right? Yeah, see, I mean, FOIL is great if you've got 2 binomials multiplying. But what if you've got a trinomial times a binomial or something else, you know? FOIL is dead to you. Let's see here. Let's see here. So let's start out with the 1 times the x squared. That gives me a half. All right? Then I'll move my way over. X times x squared gives me, well, x times x is x squared. So this is giving me minus 2, right? And then plus 2, right? All right, x cubed. So I get a 1 minus 1/6. 2 times 1/2 is 1, right? Minus 2. Where I lost my place. Okay, and then I guess that's 4/3, isn't it? Yeah. Oh, 8/6 is probably better, isn't it? Let's see here. So what do we got? We've got 1 plus x. The 2's cancel, plus 1/2 x squared, right? And what happens over here? Let's see, let me do a little math here. This is minus 7/6 plus 8/6, also known as 1/3 factorial. I did this for a reason. What is this? Can you recognize? E to the x. Very good. So this multiplication was very dumb. What we just did was very dumb from one perspective, because all I'm showing you, you see, I don't know if you can recognize this for what it is, but what I've done to you is e to the 2x times e to the minus x. See, this is e to the 2x power series. This is e to the minus x power series. And when you multiply them, you get e to the x. Es bueno. Hey, let me look at this a different way. You could take the power series, sum n equals 0 to infinity, x to the n over n factorial, and you could multiply it by the power series, sum n equals 0 to, let me say, k equals 0 to infinity, y to the k over k factorial, all right? And you can multiply these out, right? And what you would get after you collect things, using the pattern we were just doing, you'd get the sum, let's say m equals 0 to infinity, x plus y to the m over m factorial. You can do this calculation using the product of series. All you need is to define it carefully and to use the binomial theorem at each order. All right? So like, let me just do a little bit of this. 1 plus x plus 1/2 x squared, right? This. So you multiply it, you get 1 plus x plus y, right? And then how about the squared terms? What do you get for squared terms? You get xy, you get 1/2 x squared, you get 1/2 y squared. That's all your quadratic terms. You group them. That's all your degree 2 terms. And so if you rewrite that, just take a little imagination. See that, if you factor out 1/2 is 2xy. See 1/2 of x squared plus 2xy plus y squared, right? That is 1/2 of x plus y quantity squared. So there you go. There's the first 3 terms in this guy. So in other words, e to the x times e to the y is this, and that's equal to e to the x plus y. You can prove properties of the exponential using series. If you defined the exponential to be the function with this power series, which is what a lot of people do, this is taken to be basic, the starting point for the exponential, this gives you a concrete calculational way of manipulating the exponential and proving things about it. For example, it's a property that law of exponents you can prove from series. Of course, on the, pragmatically speaking, for the sake of your test and stuff, it's, you're allowed to use laws of exponents. I'm not saying you can't, all right? More power to you if you see through my subterfuge and realize I'm just asking you to multiply, here, let me try another one of these on you. See if you can see through my tactics. We definitely have more time for homework questions tomorrow. So you guys work on your homework and ask me questions. I do. If you don't work these out for yourself, they're never really going to stick for you. You watch me do these all day long, it won't really help that much. How about this? X minus 1/6 x cubed plus 1 over 120 x to the 5th plus, now you're probably on to me, so you probably know what I'm going to do. 1 minus 1/2 x squared plus 1 over 24 x to the 4th plus da da da. Let's multiply these. What do we get? Constant terms? Nothing. How about, what do we get first though? We get x, anything x squared? Nope. How about x cubed? Looks like a minus 1/6, right? Where else do we get x cubed from? Oh, this, and this, right? So minus 1/2. Anything else? Is that it? And then x to the 5th, what do we got for x to the 5th? 1/24, right? And then what else? Minus 1/12. Wait a minute. Minus? Plus 1/12, right? Anything else? Oh yeah, this one, right? Plus 120. Let's clean this up. What do we got? We've got x. What's this work out to? So I heard a minus 2/3. Is that agreed upon? Yes. All right. And this guy is 5 plus 10 plus 1 over 120. Yeah? Sorry, I'm lazy. I could think, but instead I wrote, let's see here. It depends. So let's see here. What is this? Here, let me try something and see if it makes it more obvious what it is. Multiply this by 2. Let's see here. I mean, 15 is 5 times 3, right? So 5 factorial is 5 times 4 times 3 times 2, otherwise known as 5 times 3 times 2 to the third. So this gives me a 2 to the third. I had a 2 and a 2 here already, so I've got a 2 to the fifth, all right? Oh, that's supposed to be a 3 factorial. I'm sorry. I'm like, idiot. 3 factorial is 6, not you, me. Just to be clear. All right, so what is this? Yeah, this is sine of 2x, isn't it? And you might recognize this as sine of x and cosine of x, yeah. I don't recommend this as a way to derive trig identities, personally. Like, I think the imaginary exponential stuff I showed you guys earlier is way easier, right? But anyway, the reason the point of this is not to always be looking for some hidden trig identity or something, although it may be the case it's there since it's an example I'm making. The larger point is just that this allows us to see how multiplying the series is consistent with something else we already know. All right, so it's just sort of sightseeing on top of the series calculation, which is what we're actually after at the moment. Let's see here. So I was going to show you. One last example. If I look at e to the I theta, all right? Did I already do this in here? I did? Oh, okay. I did? No? All right, well, we'll find out in a second here. So suppose that this makes sense. Nah. So you have I theta to the n over n factorial, right? And so let me just write out the first few terms and try to show what's going on here. So we'd have like 1 plus I theta plus 1/2 I theta quantity squared plus 1 over 3 factorial I theta cubed plus 1 over 4 factorial I theta to the fourth, 1 over 5 factorial I theta to the fifth. Okay, fine. How does I work? Well, like I squared is what? -1, right? And so what's I cubed? Is minus I to the fourth? It's 1 again, right? So if you look at it, we can group together, assuming that this makes sense. I will just tell you, in fact, the theory of power series is best developed over the complex numbers. There, everything we're doing gains more meaning. But these are all real because you get I squared gives you -1, or you get I to the fourth over here, which gives you +1. And so what you got is you got 1 minus 1/2 theta squared plus 1 over 4 factorial theta to the fourth plus dot 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 All right. That's all the even terms in the e to the I theta expansion. And on the flip side, the odd terms, right, they have an I, which we can peel out. So that sounds painful. Sorry, so violent. Spoiler alert. No, I won't spoiler. I won't talk about certain TV. Let's see here. Minus 1 over 3 factorial plus 1 over 5 factorial. It didn't really come out. It was just pop out a little bit. 5 to 5th plus da da da. Like that. As you can recognize, this of course is the cosine series. And over here you've got the sine series. And so here is a derivation at the level of power series. Supposing that e to the I theta makes sense, it has to be that e to the I theta is equal to cosine theta plus I sine theta. So there's another derivation of Euler's identity from power series. Right. So if you, another way to say it is if you want to make e to the I theta make sense in the same way that e to the x makes sense, you're forced to say that e to the I theta is cosine theta plus I sine theta if you want to use series calculations and everything else. So anyway, I will shut up. You guys have a good day. Tomorrow, bring me more homework questions. Aw, man, I didn't give you guys a quiz.
Yeah.
You can turn it off.